Right, question 3. The new A level is going to have questions like this, which didn't really come up very often on the old A level. This is not a question where you actually have to know some physics from before. They're going to tell you all this stuff that you need to know, and you're going to have to interpret it. So you're going to come across this equation here, which you shouldn't probably have never seen before. And the trick of doing a question like this is not to panic and just to try and work your way through it. So it's a comprehension question, and it's about unpicking a formula and interpreting some data. So the term ultrasound refers to vibrations in a material that occur at frequencies too high to be detected by the human ear. When ultrasound waves move through a solid, both longitudinal and transverse vibrations may be involved. For the longitudinal vibrations in a solid, the speed c of the ultrasound waves is given by this. Okay, so it's telling you the formula, and you're going to have to interpret it later. E is the Young's modulus and rho is the density. Values for C and rho are given into the table, so we've got glass and seawater here. Ultrasound waves, like electromagnetic radiation, can travel through the surface between two materials. When all the energy is transmitted from one material to another, the materials are said to be acoustically matched. This happens when rho C is the same for both materials. There, rho C. Okay, calculate the magnitude of the Young's modulus for glass. Right, so we need to rearrange this equation for Young's modulus. So we have C is equal to the square root of the Young's modulus divided by rho. You can either put numbers in at this stage, or I think it's probably easier to rearrange a bit. So square first, E over rho, and then rearrange for E. So the Young's modulus is equal to rho C squared. So the value of rho is just check, glass, yep. Value for rho is 2,500 times by the value of its speed is 5,100, and we've got to square that. So here goes. We have 2,500 times by 5,100 squared. Press the ENG button to get into nicer units. 65.025 times 10 to the 9, and the units of Young's modulus are the Pascal. So that is 65 times 10 to the 9 Pascal to 2SF. Okay, so that's 65 gigapascals. State your answer to 3.1 in terms of SI fundamental units. So we need the SI fundamental units of pressure. So, or Young's modulus, which is the Pascal, which is the same as pressure. So pressure is equal to a force divided by an area. This isn't the way you're supposed to present these, but I think it's easiest. So a force is a kilogram meter second to the minus 2, and we want to divide that by an area, so we divide that by a meter squared. So that is that, and that is that. How did I know that? Well, force is equal to mass times by acceleration. If we write the units of that out, mass is a kilogram, acceleration is meters second minus 2. So that's how I remember that. I just work it out from a previous formula. So that cancels with that. So you get kilogram second minus 2, then you got a meter on the bottom there, so you put meter minus 1 there. The passage states that when ultrasound waves move through a solid, both longitudinal and transverse waves or vibrations may be involved. State the difference between longitudinal and transverse vibrations. So this is a book learning question, you should just know the answer to this. So in a transverse wave, the oscillations are at 90 degrees or perpendicular to the direction of motion of the wave. Could have written velocity there, I suppose. And in a longitudinal wave, the oscillations are parallel to the velocity. So velocity is a vector, so it has a direction, so you can be parallel to it. Now, notice that I didn't just stop there. Many candidates will stop there at that answer, and they'll just say transverse waves are 90 degrees. If you are stating a difference between something, you must mention both things in your answer, so a sentence for each. Show that when two materials are acoustically matched, the ratio of their Young's moduli is equal to the ratio of their speeds of the ultrasound waves. Okay, so this is the sort of question that lots of students will just panic at because they've got no idea what to do and they've never seen it before. Well, that's the whole point. You have never seen it before, but don't panic and just work your way through it. All the information to solve it is going to be over here somewhere. So we need the ratio of the Young's modulus. So let's go back to our equation for Young's modulus that we worked out earlier. So we have E is equal to rho C squared. Now we've got two materials, so let's label up two materials, shall we? So the first material, we'll call it call it material 1, is going to equal to rho C1 squared. So that's the Young's modulus of material 1, density of material 1, speed of the wave in material 1 squared. We've also got the second material, which we can write like that. Now, I'm going to write these slightly differently. I'm going to separate out this C squared because over here I've got rho C, so I want to try and get that in because it says when they're acoustically matched, and this says this is when they're acoustically matched, when rho C is the same. So we have E1 is equal to C1 times by rho 1 C1, so I've just expanded that out. C2 times by rho 2 C2. Okay, now we need the ratio of this to this. So we need to divide these two parts by one another. So we have E1 over E2 is equal to C1 over C2 times by rho 1 C1 over rho 2 C2. So I've just taken that equation divided by that equation to find the ratio of the Young's moduli there. But for them to be acoustically matched, rho 1 C1 must equal rho 2 C2. So that's for them to be acoustically matched, so that is equal to that. So therefore they can be cancelled. I'll do that in a different colour. So you've got E1 over E2 is equal to C1 over C2, which is the answer. There are other ways you could approach that question, but I've tried to lay it out in lots of detail there. Right, finally, on this page, 3.5, the wave speed in material X is twice that of material Y. So the speed of X is equal to twice that in material Y, so that's 2c y. Okay, so that's what that sentence means in algebra. Okay, X and Y are acoustically matched. Determine the ratio of the densities. Right, so if X and Y are acoustically matched, then we know that Cx rho X must equal, using this expression here, Cy rho Y. Okay. So now what we want to do is we want to find the ratio of the density. So we want rho X divided by rho Y is going to equal Cy divided by Cx. but we've already said that Cx is 2Cy. So that is equal to, if I replace Cx with 2Cy, I'm going to get Cy divided by 2Cy. So the speeds cancel and I'm left with a 1 there. And I've got the ratio of rho x to rho y is 1 to 2. So that's 1 to 2. And that's that section there. Right. Question 3, part 6. Ultrasound waves obey the same laws of reflection and refraction as electromagnetic waves. Using the data from Table 1, discuss the conditions for which total internal reflection can occur when the ultrasound waves travel between glass and seawater. Okay, so total internal reflection occurs when the wave is trying to travel from somewhere where the speed is slower to somewhere where the speed is faster, so it's got to be going from seawater to glass. So TIR could occur if the wave is trying to go from, it's got to be from the water to the glass. Can't be the other way around, otherwise it'll just refract normally. So, and for the other condition for total internal reflection to occur is the angle of incidence has to be bigger than the critical angle. And the angle of incidence must be larger than the critical angle. Okay, so the equation to work that out is sine of theta c is equal to the ratio of the speeds in the two materials. So it's got to be the slower one on the top and the faster one on the bottom. If you got those the wrong way around, you'd find that you got an error when you did this on your calculator, so you'd know to flip it up. So 1/400 from there divided by 5,100. So sine theta c therefore is equal to 1/400 divided by 5,100, which is that. And then we want theta c is got to equal the inverse sine of that. So we do shift, sine, press answer, and we get 15.9. And that's in degrees. Okay, so the angle has to be bigger than that, and it has to be trying to go from the water to the glass. Right, I'm going to do a bit of a side now to figure out, if you didn't know that, what you could do. Okay, so on the formula sheet that equation isn't actually quoted, so what we can do is we can work out what the refractive indexes of these, or the refractive indexes of these two materials are in relation to one another using this information. It's a little bit faffy, but we can do it. So we have the N of water is equal to the speed in some constant medium, so with light that's the speed in a vacuum, divided by the speed in the water, and we have the same thing for glass. It's equal to the speed in whatever divided by the speed in glass. Now what I'm going to do is I'm going to divide those two equations by each other to get the ratio of N water to N glass. So NW over NG is going to equal C over CW divided by C over CG, glass. So to divide by a fraction, we flip the fraction up, CG over C, and multiply. those two cancel, so we have the ratio of the two refractive indices is equal to the inverse of the ratio of the two speeds. So here we have theta c, sine of theta c is equal to the refractive index of glass divided by the refractive index of water. So we'll need to flip this fraction over, won't we? So we've got Ng over Nw is equal to Cw over Cg. So that is equal to Cw over Cg sine theta c. So that is what I used over there. But remember, if you get that the wrong way round, you just get an error. So here you get 5,100 divided by 1400. You try and do the inverse sine of that, and it comes up with an error. So you know you've got your fraction the wrong way up, and you can just go and fix it. Right, that was a bit of an aside, but I think it's probably useful. So that's the whole question in full. Okay, that's question 3 done.